times V2 minus V1. So if AOD is very large, then we can say that V2 minus V1, therefore V2 minus V1 is given by V0 by AOD. And if AOD is very large, then V2 minus V1 tends to 0. Therefore, V2 minus V1 tends to 0. And therefore, we say that the two input terminals, V1 and V2, are virtually shorted. We use this word, they are virtually shorted. Why it is virtually shorted? It is called virtually shorted because in reality, they are not shorted. We are not connecting a wire from here to here. In reality, they are not shorted. But they are virtually shorted because their potential difference is 0. Okay. We also named a common mode signal to be the case when V1 equal to V2, and which is non-zero. And we know that if V1 equal to V2, a simple like calculation shows that the output voltage will be 0. So if V1 equal to V2 which is not equal to 0, it is called the common mode input signal. The V1 and V2 are called common mode input signal, and the corresponding V0 is called the common mode output signal, which is ideally 0. So let us consider the characteristics of the other characteristics of the operational amplifier. One characteristics we already know, that the open loop differential voltage gain is infinite. The internal differential gain. This is the internal differential gain of the operational amplifier. Internal differential gain. And therefore, we also noted right now that V2 minus V1 tends to 0. Or it is assumed to be 0. So the two input voltages V1 and V2 are nearly equal. The other important characteristics of the operational amplifier is that the input impedance to the operational amplifier the effective input resistance, I should say resistance because it is resistive. The input resistance looked at the operational amplifier, that is the resistance looked upon by this voltage source and the resistance looked upon by this voltage source, they are both infinite. So the input resistance to the operational amplifier is infinite. And what is the result? So the input resistance goes to infinity. And thereby, what is the result? If there are two currents here, the current here is I1, the current here is I2. We can write I1 is equal to 0, I2 equal to 0. Because the input resistance seen by the voltage sources V1 and V2 are infinite. So the input currents to the inverting and the non-inverting input terminals, the input current to terminals 1, input terminals 1 and 2 to the operational amplifier are 0, both 0. The output resistance similarly of an operational amplifier.
Can you repeat this?
So V1 and V2 in essence, see V1 and V2, they are the two input sources. They are looking at infinite input impedance or infinite input resistance, so to say. So this V1 is looking at an infinite input resistance. This V2 is looking at an infinite input resistance. So if V1 is looking at an infinite input resistance, if there is a source V1, consider this source V1, if it is looking at an infinite input resistance, that means it is open circuited. To V1, the connection number 1, this is terminal 1 of the operational amplifier. Whatever is lying here whatever this is lying here does not matter to V1 because it is open circuited. So therefore, open circuited means it is looking at an input impedance Ri to be infinity, and therefore this current, there will be no current flowing because it is open circuited. The entire voltage here V1 falls here. Whether this V1 might have a resistance.
Sir, how Ri tends to infinite? That is my question.
Can you repeat your question?
Sir, how Ri tends to infinite?
That question we are not going to address because that is dependent on the good question, but that is dependent on the input, what is lying inside the operational amplifier. Thus, it is the job of the circuit inside the operational amplifier to ensure that Ri is infinite. How the operational amplifier achieves this goal, that we are not going to address. Just as we are not going to address how the voltage in terminal number 3 becomes AOD times V2 minus V1 when AOD is very large. There also you could ask the question, how is this happening? And this is a very valid question. But unfortunately, we are not going to discuss this for the very precise reason that we are saying that the operational amplifier to me is a black box. In this course, in this very basic course, the operational amplifier is a black box. Okay. In fact, there are two supplies to the operational amplifier. One is a positive supply, another is a negative supply. Okay. So how and why, that we are not going to. We are saying because that will entail understanding what is inside the operational amplifier, which is much outside this course. We need a very thorough understanding of transistors and transistor biasing, multi-transistor configurations to understand that. Okay, not done in a basic course like that, like this. So it is much outside this course purview. So, but what we do understand, what we do need to understand is, given this three-terminal device, what we are essentially doing in this course is that given this three-terminal device, let us assume that the three-terminal device has these characteristics. Then how can this device be put to practical use? That is the question we are going to address in this course. So then what are the characteristics of this device? We are just examining. Okay, so this is the third character of the operational amplifier, which is that the input resistance goes to infinity. The fourth character of the operational amplifier is that the output resistance goes to 0. It is very low. So this is R0, the output resistance. So that means what? The output load. So the output voltage here is the output voltage. So here is the output voltage V0. It is directly connected to the differential voltage source or the dependent voltage source. And the output voltage V0 will be independent of any load which is connected here. If you connect a load here, this output voltage V0 is not going to change, because the output resistance, which is the resistance here, this is the resistance R0. Let us not like clutter up this figure. Let me draw more. And this is my output. So here that means it is connected here. So if you look at from this side to this side, this is the resistance R0, that is 0. That means if you connect a load resistance here, because this output is 0, this V0 is going to be independent of this load resistance. If there was a finite resistance here, if R0 were not 0, then when you connect this load resistance, the output voltage V0 will be a function of this load resistance, because the current will depend on the load resistance and the potential drop across R0 will be dependent on that current. Understood? So therefore V0 will be dependent on the load resistance RL, because this current will be dependent on RL, and this current dependent on RL means the PD across R0 will be dependent on RL, and therefore V0 will be dependent on RL. But since R0 is 0, sorry, this is R0. Since R0 is 0, the output voltage V0 will be independent of RL, because there is no drop. So as I said, the entire differential output voltage AOD V2 minus V1 falls here. V0 is AOD V2 minus V1 regardless of RL. So these 4 important characteristics of the operational amplifier need to be carefully put in mind.
Sir, can you repeat this dependent and independent?
Yeah. The point is that the resistance looking from the output towards the left hand side, this resistance R0, which is the resistance looking from the output towards the left hand side, is 0. What does this mean? This means that if I connect a resistance load, if this operational amplifier is driving a load, this load is RL. So you see that if the output resistance R0 as is depicted here, if the output resistance R0 were not 0, if it was a finite value, then obviously the current in this loop, the current will be dependent on R0 plus RL, and it will be dependent on RL. And therefore the potential drop across R0, which is IR0, will be dependent on RL. And therefore the output voltage, V0 will be dependent on the potential on RL. Because V0 is nothing but AOD V2 minus V1 minus I times R0, and I is dependent on RL. Therefore V0 is dependent. Very simple. Therefore V0 will be dependent on RL. But if this R0 goes to 0, if this R0 is not 0, then whatever load resistance you connect 5 ohm, you connect 100 kilo ohm. Whether RL is 5 ohm or 100 kilo ohm, does not matter. The output voltage V0 will stay at AOD V2 minus V1. So there is no loading effects. This is always desired of the output resistance, that there are no loading. We always want that the output voltage V0 should not be dependent on the load resistance. There are no, we call this, there are no loading effects. Whether you connect a small resistance or whether you connect a large resistance, the output voltage V0 is the same. The driving volt, because V0 is driving the load, so that V0 is constant, should be constant. Okay, you connect a bulb. Okay, depending on the wattage of the bulb, the input voltage to the bulb itself differs. So that is not very desired. Okay. See, always we want the input resistance of the output resistance of a source to be 0, because then the entire source voltage falls here. Okay, that is always needed. Here it is not needed, because anyway the input resistance looked at here is infinity. So here the current is 0. Whether the source has a resistance, big resistance, or whether the source has a small resistance does not matter, because anyway the source is looking at a situation like this. This source is looking at a situation whether there is a small source resistance, whether this is again 5 ohm or 1000 kilo ohm. It does not matter, because anyway it is connected to open circuit. So this current will be 0. We will see that these characteristics play a very important role in the job the operational amplifier needs to perform. Though it seems that the operational amplifier itself is composed of a rather complex transistor arrangement inside, the operational amplifier is one of the cellular components of larger integrated circuits. I mean, old integrated circuits. Now the concept has much more evolved and much more changed, with levels of integration that are very, very high, but they are the cellular components. Okay, they are the cellular components, or they are the individual components. They are the basic building blocks of larger complex integrated circuits. That is what we are going to investigate here, what the operational amplifier does, not how it does it. Okay, so let us take the first example, a very simple example called an inverting amplifier. As I said, working with operational amplifier is on the circuit level very easy, because once you know the properties, it is relatively very easy to analyze an operational amplifier. We have a resistance here connected to the inverting input, and this terminal, the non-inverting input, is connected to ground. So we have two bunches resistors, one connected to the input, and R2 is called the feedback resistance because it is connected from the output to the input. So we can say that I1 here, because this terminal and this terminal are virtually short, we can say I1 equal to Vi minus, let's call this V1, let's call this V2, Vi minus V1 by R1, and that is Vi minus 0 by R1, that is Vi by R1. And V0, because this current I1 will also flow through R2, so the current here will also be I1. If this current is I2, if I can say this current is I2, or we can let me write this as I2, I can write I2 equal to I1. Why? Because here the current is 0, I equal to 0. So all the current which is coming here has to flow there, because there is no input current here. So I2 equal to I1. So therefore, V0 will be equal to V1 minus I1 R2. You can write I2 R2 equal to I1 R2. That is V1 is 0 minus what is I1? This is I1. So Vi by R1 times R2. And therefore, what is V0 by Vi? Which is what is needed. It is called AV. It is the closed loop voltage gain. The word closed loop comes from the fact that we have now a feedback loop in place from connecting the output to the input. That is why this word closed loop. Differentiate it or distinguish it with the open loop where the output was not connected to the input. In this case, we have the open loop voltage gain. AOD is the open loop differential gain. See this word open loop. Open loop means that the output is not connected to the input. It is the internal, we also said that AOD is the internal differential voltage gain. Because it is inherent to the operational amplifier. It is dependent on the operational amplifier. What is inside the operational amplifier? And it is infinity. It is very, very large. So this is the open loop or the internal differential voltage gain. Open loop because the output is not connected to the input. Distinguish it now with what we have now. It is the closed loop voltage gain because now we have connected, we have a feedback path. So this path is called a feedback path, connecting the output V0 to the input terminal 1. So this is called a feedback path. So therefore, we say the closed loop voltage gain. What will be V0 by Vi? We just calculate from here, very simple. So V0 is minus Vi R2 by R1. So AV equal to V0 by Vi equal to minus R2 by R1. As simple as that. So you see, it is called an inverting amplifier because the output is out of phase with the input. V0 is equal to minus Vi R2 by R1. So it is dependent on the the output is 180 degree out of phase with the input. Note also the difference between the open loop and the closed loop voltage gain. This is dependent on only the external resistances. There is no sign of what is inside the operational amplifier. Note this important character. Now we are going to divorce ourselves from what is inside the operational amplifier. That is not material to us anymore. To us, the operational amplifier will always remain as a black box. It is a black box.
Excuse me, sir.
Yes.
Sir, V1 is 0 because it's virtually shorted.
Yes. Yes.
Okay,
V1 is 0 because it is virtually shorted to V2. Okay. So AV is minus R2 by R1. So therefore you see that the closed loop voltage gain is dependent on the external resistors. Why is this phenomenal? This is a revolution. Remember, if you remember your transistor days, your BJT, what we learned about the BJT, we learned about the MOSFET, we went through all those complex expressions of gain when we have even a single transistor, a single C amplifier. You add a bias resistor, we have a whole bunch of like expressions, GM, R pi, and all those things, they come inside the gain. For the MOSFET, device characteristics come inside the gain. They come inside the gain. Gain, they come inside the gain expression, but in the MOSFET we did not do the small signal analysis, but it will come. Okay, but if you distinguish, at least take the BJT, which we have done. So if you distinguish that with the operational amplifier, you see the important achievement. That is, the voltage gain is to the user's control. Now, what we have achieved by making AOD infinite is that we have divorced ourselves. We have divorced ourselves from the operational amplifier, the circuit inside the operational amplifier, and therefore the voltage gain is in my control. It is totally in my control. I change R2 and R1, which are added by me. I can change the voltage gain. Therefore, it is totally, things are totally in my control. An important parameter like voltage gain comes totally in my control is a very big achievement. You know that now, because they have done the circuit analysis, the small signal analysis of the BJT. So this is a very important achievement. And this we are achieving because of these 4 important properties of the operational amplifier. So these 4 properties are phenomenally important. Now we can also determine the input impedance seen by the source Vi. What does this source see? If this is the current I1, the input resistance seen by the source Vi will be Vi by I1. So I1 will be Vi. We'll write it. So the input resistance seen by the source, see, why it is Vi by R1? We have seen this. This is I1. It is Vi by R1. So the input resistance seen by the source, which is R1, which is Ri. It is the input resistance seen by V1, seen by the source V1, that is Ri, that is equal to R1. So this is Vi by Ri, you can say. That is equal to Vi by R1, as we have seen here. So again, you see that the input resistance seen by the source has nothing to do with the operational amplifier. It is a function of the external resistor only. This is again a very important achievement. Again, you recall your BJT chapter. There you calculate, if you have to calculate the input resistance seen from the base side, you will find that all those resistances R pi and all those things will come in. But here nothing is like that. There is no sign of any device characteristics. Everything is user dependent. Everything is under the control of the user. So the op-amp gives everything to your control. You can control everything. This is a very important and a fundamental achievement why the operational amplifier is the building block towards achieving other circuits. Because what is inside the operational amplifier is no longer important to me. That is why the operational amplifier is a revolution in circuit theory. because of the four characteristics of the operational amplifier, from which it will see how it manifests itself in useful component design. And we also know that we talked about this before, that there are no coupling capacitors here. There is no coupling capacitor in the operational amplifier, so the voltage V1 and V0 can be DC voltages. The voltages, currents, everywhere, they can be DC currents. They can be DC voltages, they can be DC currents. VI, input voltage VI, output voltage V0, the currents I1 and I2, they can also be DC currents. So the operational amplifier can also amplify DC voltages. So this is one example of the operational amplifier, how it performs. Now you see that if I use this circuit to realize a gain, let us say I want to realize a gain of AB, a closed loop voltage gain, AB equal to -100. And we have the input resistance of the source, which is R1, as 50 kilo. A simple calculation will show, because AB is given by -R2 by R1. AB is given by -R2 by R1, you can see here. So simple calculation will show the value of R2 will be very large. The value of R2 will be how much? It will be 5 mega ohm. R1 times AB, 50 kilo ohm times 100, 50 into 10 to the power 3 into 100. So that will be 5 mega ohm. But this resistance will be too large for practical realization. So what to do? So here comes the next design which solves this problem. It is called the amplifier with a T network. We have again the simple operational amplifier. We have VI here, R1 here, R2 here, R3 here, R4 here. So we have the currents I1, I2, I3, I4, and the potential here is Vx. All we need to find is always for the operational amplifier, usually for the operational amplifier, what is the value of the closed loop voltage gain, V0 by Vi? In 99.99% cases, we need to find out this quantity. So it's very simple. Again, we apply the same principle. These two terminals are virtually shorted. So 1 and 2 virtually short. So therefore, this comes to be ground. So therefore, I1 becomes equal to Vi by R1 because V1 is at zero potential. So and that is equal to the Vi by R1 and that is equal to I2. And then we can find that the voltage Vx 0 minus I2 R2. So Vx is given by 0 potential V1 minus I2 R2. That is minus Vi by R1 times R2. We also have I2 plus I4 equal to I3. And what is I2? It is 0 minus Vx by R2. So minus Vx by R2. What is I4? Vx minus V0, I4, 0 minus Vx by R4. So minus Vx by R4. And what is I3? Vx minus V0 by R3. So you see how simple operational amplifier circuit analysis is. It is nothing. Once you know the characteristics, it is nothing. It is one of the simplest things probably you can do. Okay. But please again, I will ask you, please practice. So therefore, equal to V0 by R3. Just check whether I'm writing correctly. Okay, some minus or pluses and everything like that. And then we know what is the value of Vx in terms of Vi. So Vx is known in terms of Vi from here. So substitute Vx from here. Minus Vx minus Vi R2 by R1. Once you do that, so substitute Vx from there. And once you do that, you'll find AV. That is minus R2 by R1 So now you see how the value of AV is controlled by not only R2 by R1 by linear scale, but it can be tailored. All these resistances can be tailored to appropriately realizable values, not extreme values, by the incorporation of the T network or by the incorporation of R3 and R4. So by using these resistances, we can realize
R3 in numerator.
Tell that again.
Sir, because there is V0 by R3. Sir, sir in the voltage gain R2, R3 by R1.
minus
Oh,
R2 by
leave it in R.
R1.
Okay, sir, I understood.
Yeah, it is correct. It is correct. Just work it out. R3 multiplied, it will be 1 R3 by R2 and R3 by R4. Simple. So you see how the values of R3 and R4 can be selected properly in order to make all these resistances come within realizable values to achieve a particular gain for a given value of R1. So now we have three resistances at my disposal, R2, R3 and R4, which can be tailored to bring these resistance values at within realizable practical limits. So this is called the amplifier with a T network. Next we come to an amplifier with a finite gain. Or we can write effect of a finite gain. That is probably an apt way to write it. Which means that in this case we are not going to assume that the open loop differential gain is infinite. We are not going to assume. So therefore we will say that the two input terminals will also not be virtually short circuited. So we have a resistance R1 connected to terminal 1. The inverting amplifier configuration, which we wrote, R2. And this is V0. And this is connected to ground. This is terminal number 2. So now V0 will be AOD V2 minus V1. So we cannot assume, therefore, we cannot therefore assume, and therefore we cannot assume that the two input terminals are virtually short. Because if AOD V2 minus V1 is V0, and if AOD is finite, V2 minus V1 does not go to 0. So we cannot assume that. So V2 is not equal to V1. Therefore, V2 is not equal to V1. So here is V2, there is V1. Please be careful. As soon as the effect of a finite gain is there, V2 does not become equal to V1. So we use the general expression. V0 equal to AOD V2 minus V1. So now, what happens? Here is my I1. So here is my VI. Here is my I1. There is my I2. I1 and I2 is still 0. And the current here is still 0. I should say, what should I say? Let's call this IX, IX1. that is feasible. So we can write very simple. I1 is Vi minus V1 by R1. So this is not Ri, this is R1. Okay. And the current through I2 through, oh sorry, we have to call this I2x. So this current is I2. R2. And we know that I1 equal to I2. That too you know, because the input resistance is still infinite. And VO is given by AOD times V2 minus V1. V2 is 0 and V1 is V1. So it is given by minus AOD times V1. So the V1 is otherwise given by minus V0 by AOD. And now combining I1 equal to I2, we eliminate this one, V1, equating I1 equal to I2. Since I1 equal to I2, we write I1 Vi plus, we substitute from V1 here, basically eliminating V1, nothing else. Plus VO by AOD times I1 R1 equal to I2, and we substitute from here also there. Then replace V1. And then solving for V0 by Vi from this expression. So AB is given by V0 by Vi, V0 by Vi, that is minus R2 by R1, 1 by if AOD approaches infinity, this term approaches 0 and AB approaches minus R2 by R1, which we found out for the inverting amplifier. Ideal operational amplifier, then AB becomes equal to minus R2 by R1. So now we come to the first application of the operational amplifier called the summing amplifier. The first, I would say, the first mathematical operation of the operational amplifier. So it is nothing but a set of input resistors connected to the inverting operational amplifier configuration. So we have the inverting operational amplifier. Instead of connecting one resistor, we will connect a set of as many resistors we like to, as many voltage sources we like to add up. So here it will be VI1, VI2, VI3, R1, R2, R3. I1, I2, I3, I4. We simply use superimposition or superposition. So we set Vi2 equal to Vi3 equal to 0. And then we know the current I1 is given by Vi1 by R1. And V0 with only Vi1 source working will be equal to minus I1 RF, 0 minus I4 RF is V0. 0 minus I4 RF, and I4 becomes equal to I1 because the Vi2 and Vi3 sources are not working. So I4 becomes equal to I1, so it becomes minus I1 RF. And I1 is given by Vi1 by R1, so that is equal to similarly with the sources.
Vi2 and Vi3 are 0.
No. I according to superposition theorem, if I have a circuit, let us say a circuit where 2 voltage sources are working or 3 voltage sources are working. According to superposition theorem, the current through this resistance R1 is the summation of if V1 is only working alone in the absence of V2 and V3, and absence means V2 equal to 0, V3 equal to 0. So if it is the current through this resistance R1 is the current if V1 alone is working plus the situation if V2 alone is working plus the situation or plus the current if V3 alone is working. This is always true. Regardless of, here we have very simple series configuration, but it is always true for any configuration. This is called the superimposition theorem or the superposition theorem. Okay, so therefore, if I find the total current through RF, want to find out the total current through RF, I can find out the current through RF first assuming Vi1 is working with Vi2, Vi3 0. Then I will add that current with the situation where Vi2 only is working with Vi1, Vi3 equal to 0. And then add the current with Vi3 only working with Vi1 and Vi2 equal to 0. This is the statement of the superposition theorem, which is applied in this low frequency circuit analysis, and it is also applied in high frequency circuit analysis in a much more complicated form, because there you have integral and differential equations. But anyway, let's keep that aside. But the reason why I brought that was superposition theorem is a very important principle in circuit analysis, and eventually in Maxwell's equations or in field analysis, where we have electric and magnetic fields. There, the ramification of this method is called the method of scattering superimposition. Okay, so it is a very important circuit analysis tool. So then V0 due to Vi1, for instance, is minus Rf by R1 times Vi1. So this is Vi1. Similarly, V0 due to only due to Vi2 working will be minus I2 Rf, and that is minus Rf by R2 into Vi2, and V0 due to Vi3 working will be equal to minus I3 Rf. Minus I3 Rf, that is minus Rf by R3 into Vi3. So R3. So the total V0 becomes minus Rf by R1 into Vi1 minus Rf by R2 into Vi2 minus Rf by R3 into Vi3. That is, the voltages due to Vi1 only working, the voltages due to Vi, the voltage due to Vi, output voltage due to Vi2 only working, plus the output voltage due to Vi3 only working. So this is the total output voltage if all three voltage sources are working simultaneously. So you see that this is the sum of the input voltages multiplied by a weighting factor, or multiplied by different weighting factors, minus Rf by R1, minus Rf by R2, minus Rf by R3. So this is called an inverting summing amplifier. Why? Because of this minus sign, which we can take common. That is why it is called inverting. Note this minus sign. And we can increase the number of terminals here. The number of input voltage terminals, we can have Vi4, Vi5, Vi6, Vi7, as many number of voltages, they will be added with their corresponding weights. And now we set, if we now set R1 equal to R2 equal to R3 equal to R, then V0 becomes equal to minus RF by R or minus RF by R1, whatever you can call, Vi1 plus Vi2 plus Vi3. Simple. So the output is the summation of the three input voltages with a common multiplying factor minus RF by R1. Okay, this is called the single amplifier. The output is the input summation of the input with a single amplification factor. How the operational amplifier can be used to do simple mathematical operations, just like adding voltages. But they can perform many other operations, as we see, other than mathematical operations. That is not the only thing operational amplifiers perform. Operational amplifier can perform mathematical operations as well as many other operations. We already saw some operations like the inverting amplifier, and we'll see some more. Okay, and in addition to just adding up voltages, operational amplifiers can also be used to integrate and differentiate. To integrate and differentiate. Both these operations can be performed by an operational amplifier. Okay. So now we slowly realize how more complex circuits can be built with the operational amplifier. So now we come to the non-inverting amplifier. We saw the inverting amplifier. So that is, the output will be in phase. The output will be in phase with the input, not out of phase with the input, as in case of the inverting amplifier. So if I have a slight modification to the operational amplifier circuit, and this is again terminal 1, terminal 2, I1. So what here? Zero minus V1 by R1. So here is V1, here is V2, and V1 is nothing but V2, and V2 is nothing but Vi. So that is minus Vi by R1. Current I2 will be given by V1 minus V0 by R2. that is Vi minus V0 by R2. Then we just apply I1 equal to I2. If we just apply I1 equal to I2, we can get V0 by Vi. As simple as that. And from which I can find out my AV. And it will work out to be 1 plus R2 by R1. So you see the output is in phase with the input. Therefore, V0 is in phase with Vi. Hence the name non-inverting amplifier. And the voltage gain is also greater than unity. AV is greater than 1. It is 1 plus R2 by R1. Then we come to another circuit application called a voltage follower. And at first sight, it may appear to be of little use. We have a source voltage Vi. It is connected here. And we simply short the inverting terminal with the output. It is V0. So therefore, AV becomes equal to V0 by Vi. So Vi falls here, means Vi falls here, because the input and output are shorted, virtually shorted. And Vi equal to V0, because they are just shorted together. So Va0 by Vi equal to 1. So what is the big deal? What are we achieving? What is the purpose? I can as well short V0 and Vi. No operational amplifier, I can just short V0 and Vi. Vi and V0. We just short together. What is the need of all these operational amplifier in this? So this circuit is also called an impedance transformer. And there is a reason why this is called impedance transformer. Or it is also called a buffer. Imagine that I have a signal source with a very high output impedance, and it is driving a load with a very low load impedance or a load resistance. Say I have a voltage source Vi. I told you normally it is expected that the output impedance of a signal source be very small. But let us say things are not in my control. It may be a transducer. like like a resistor which is dependent on the value of the resistance is dependent on the temperature. We might want to measure temperature, and therefore we might devise a resistor which is dependent on the temperature. The resistance value of the resistance changes with temperature, and we sense the change in resistance to sense the temperature. So these are transducer applications. We want to measure temperature, we want to measure the level of illumination, we want to measure the soil moisture content. Okay, so things which are taking into account or which take into input one parameter like a soil moisture or temperature or illumination level and convert it to an electrical signal are called transducers. So then we can measure the change in electrical signal and relate that change with the original parameter which is causing the change to measure that parameter. So this is a very commonly used tool to measure things in the real world. So for such transducers, let us say we do not have, we can design a voltage signal, voltage source with a low output resistance. But for transducers, we do not have control over them. So let us say its source resistance is 100 kilo ohm, and we want to drive a load. The load impedance of the load resistance is 1 kilo. So what is going to happen to the voltage here? So V0 by Vi will be RL by RL plus RS, and that will be 0.01. So therefore, almost the entire source voltage, that is V0 is 100th times Vi. So almost the entire source voltage is spent in the drop across this resistance, leaving precious little at the output to drive this load. The entire source voltage is expended as a PD drop across RS. So this is called the loading of the output source output voltage V0. It happens because things are exactly opposite as to what is desired. We should have a situation where RS is very small. As I told you, in the operational amplifier, the RS is the output voltage, the output resistance is very small. So RS should be very small, and thereby the drop across RS should be minimal, and thereby this voltage Vi should fall totally as be same as V0. And that is exactly where the voltage follower walks in, because if I now connect this same output the same input signal, the input voltage with this source resistance here, RS has 100 kilo ohm to this point, and then connect this with the output. The RL as 1 kilo ohm load. Then you see the entire voltage Vi falls here, because the input resistance of the operational amplifier is much higher than 100 kilo ohm. The input resistance which is seen at this point to the right side, it is much higher than RS, equal to 100 kilo ohm. Therefore, almost the entire voltage, ideally actually the entire voltage Vi falls here. And if Vi falls here, Vi goes there, because the two terminals are virtually shorted. And if Vi goes there, Vi goes there. So you see, regardless of the source impedance, the source resistance, the output voltage V0 becomes equal to Vi and not 0.01 Vi. So the loading effect is almost totally eliminated. So this is the job of the impedance transformer. It is because it transforms the impedance, so to say. It solves the impedance problem. So this is a very, very useful circuit component, because there will be many, many situations where the source resistance is not in your control. And you have to drive a particular load because this is given by the vendor to you. This is usually provided by the vendor that you have to drive this load. Such a rated current should flow through this load. So how do you do that? Because if you directly connect, there will be severe loading effects if the source resistance is high. So then you connect a buffer or an impedance transformer in between to effectively eliminate the loading effect. Okay. So the next circuit we will discuss is the current to voltage converter. That is, we want an output voltage which is proportional to the input current. We want the output voltage which is proportional to the input current. We will need this for many applications. So the input signal, input information is given by the current, and we want to convert that to a voltage because we want to process the voltage, not the current. Okay. From a measuring instrument, we get a current which is proportional to the quantity to be measured. Now we want to deal with the corresponding change in voltage and process that sense the change in voltage, which will be proportional to the change in the measuring conditions, change in the original parameter. So the current is being generated by the changed parameter. Let us say again, light falling on a device. Then the current through the device is changing. I want to convert the changing current to a changing voltage because I want to measure the changing voltage. So there I will need to convert the current to a voltage. And what do we mean convert? This word convert means we generate a voltage which is proportional to the current. When the current changes, the voltage proportionally changes. So we have a current source. Directly connected to a resistance. I mean, this is a parallel resistance of the current source. And this is connected to operational amplifier. So we know V1 equal to 0. So this can be a photodiode, as I said, that basically by light falling on this device, the current changes, or photodetector. So we want to convert this output current IS. Then output voltage. So the input resistance Ri looked at here. So this is Ri equal to V1 by I1. That is equal to 0. So RS is very much greater than Ri. RS will be very much greater than Ri. Therefore, the current I1, therefore the current I1 will be approximately equal to IS. Then we can write that I2 equal to I1 equal to RS. Therefore, I2 equal to I1 equal to IS, and V0 is nothing but minus I2 RF, that is equal to minus IS. V0 will be minus I2 RF. So you see that the output voltage is proportional, as simple as that. The output voltage is proportional to the input current, is IS. Okay. So this is simply how a current to a voltage converter works. The input signal IS is converted to an output voltage, which is proportional to the input signal current. So we can have another circuit which does the reverse thing, which is the voltage to current converter. So if I have a circuit like this,
go back to previous page once.
Yes. Not here. Yeah.
No, sir. Final result is it? Okay, sir.
This one I could not hear you. What?
Yes, sir. I couldn't note, so I just wanted to note it once. Thank you, sir.
Yeah. Okay. So again, this is Vi, this is R1, this is R2, and this is a current source. In a better way. The current source. So here we have, if this is I1 and this is I2, we have I2 equal to I1 equal to Vi by R1. And therefore V0, we know that V0 is equal to minus I2 R2. So V0 is given by minus I2 R2. That is equal to minus Vi by R1 into R2. So you see that the current I2 is directly proportional to the signal voltage Vi. And it is also independent of R2. It will also be independent of R2 or any load voltage or load resistance connected at the output. The current I2 is proportional to Vi and is independent of either R2 or any load resistance which is connected to V0. But in this case, we do have what we do have is that the load, one side of the load impedance is not a ground. So one side of the load impedance is, we need to have one side of the load impedance at ground potential. So the current is flowing through the load impedance R2, but we need access to one side of the load impedance which should be ideally grounded, because usually we want one side of the load impedance to be grounded. So this circuit may not be practical for most of those applications. Okay, because R2 is not connected, the R2 or the load impedance is not directly connected to ground. It is connected to virtual ground, but it is not directly connected to ground. So for that, I mean, R2 is the load impedance, which is, it should be said that it is not directly, the load impedance R2 is not directly connected to ground. So in order to achieve that, we need to relatively add a bunch of different resistors. You can say that I2. And that is I1. And this is Vi. This is R3. This is I3. This is IL. This is sorry, let's call this I4. And the current here is 0. So V1 again, V2 again. So V1 equal to V2 and that is equal to VL, which is the voltage here, and that is equal to ILZL. The current I1 VI minus ILZL by R1, and that is equal to I2, and that is I2. And what is I2? I2 is V1, that is ILZL minus V0 by RF. And if we sum up the currents at this terminal, we have I3 equal to IL plus I4. So V0 minus VL by R3, and VL is ILZL. We can replace this by ILZL. That is equal to IL plus I4 is VL, again ILZL by R2. So if you substitute from V0 minus ILZL from here, from this equation, what is the value of V0 minus ILZL? From this equation, if you substitute here, we will get RF by R1 ILZL minus VI. This is nothing, plain circuit theory, okay? That is IL plus ILZL by R2. So now if I find out the value of IL or combine the terms with only IL, we get ZL by R3 minus 1 minus ZL by R2 equal to VI RF by R1, R3. Now we want to make IL independent of ZL. Because we want that the load current should be independent of the load impedance and will be dependent on the or proportional to the input source voltage Vi and independent of the load impedance. So if we want to achieve, right, rather than you write, if we want to achieve, that IL be independent of ZL, we will make the coefficient of ZL to be 0. The coefficient of ZL can be 0. Of ZL is to be made 0. That is RF by R1 by R3 is equal to 1 by R2. That is, we want to make RF by R1 R3 equal to 1 by R2. And if that be the case, so in that case, IL becomes equal to and that is equal to minus Vi by R2 from this relationship. RF by R1 R3 is R2. So the load current is proportional to the source voltage or input voltage and is independent of the load impedance. So this achieves a voltage, a voltage to current converter is connected to ground. Okay, so this is another example of a measuring circuit, a circuit which is used to measure quantities, namely a current to a voltage converter or a voltage to a current converter. So next we have a circuit called a difference amplifier. We saw that the amplifier already amplifies the difference between two signals. We saw that the amplifier already does this job. But we want a difference amplifier such that this amplification factor is in my control again. It will depend only on the resistance values which we are adding external. So any kind of information, as I said to you, any kind of information signal which is here, any kind of information signal here, they will be corrupted by noise. So if, for example, this is a signal which is coming, an audio signal which is coming, and it is converted to an electrical signal, so that will be there can be a common noise here. So when I amplify, so that noise gets cancelled out. We mentioned this in our first class. So now we want the output between two input signals, but it will be independent of AOD. It will be totally dependent. The gain will be totally dependent on the external resistors added. Thereby, we can control the gain. As I said, we want control over the circuit. Once the device is manufactured, okay, we now want to say that we will connect things to the circuit and want to control the device characteristics. The more a device can be controlled by the user, the more powerful and versatile that device becomes. Please keep this in mind. That's where the versatility and power of the operational amplifier, because we have now control. The user has total control over the device. He can control the gain. He can control the closed loop gain. Everything is in his control. So that makes the operational amplifier particularly useful. So remember that. So we have a circuit like this. Okay, so these are the two voltages VI1 and VI2, and now again we will use superimposition principle or the superposition principle. We'll first set VI1 0, find the circuit output voltage V0, and we'll set VI2 equal to 0. I mean VI1 equal to 0 with VI2 working. Okay, one case, and find the output voltage V0, and then I will set VI2 equal to 0 with VI1 working and find the output voltage V0, and then I will add up the two responses in order to find out the output voltage V0 when both VI1 and VI2 are working. So I again repeat. For one case, we set VI1 to be 0 and keep VI2 working, find the output voltage V0. For the next case, we set VI2 working, or sorry, VI1 working with VI2 equal to 0, find the output voltage. Now, the case where VI1 and VI2 are both working, if I want to find out output voltage V0, it is the addition of those two previous voltages, previous output voltages. So if I set VI2 0, we have a simple circuit. Whatever we connect is 0 here, so this is 0. So we call this V01. So V01, because it is nothing but an inverting amplifier. So there is 0 here, means there is 0 here. So this point is grounded. So this is nothing but an inverting amplifier. It is minus R2 by R1 minus R2 by R1 VI1 minus R2 by R1 times VI or VI1. Okay, let's write it a little bit better. Now we set VI1 to be 0. If I set VI1 to be 0, it becomes a non-inverting amplifier. If I set VI1 equal to 0, it simply becomes a non-inverting amplifier. Make the same rule. Let's keep this VI. Okay. Should not mix up the symbols. So this is VI. So this is VI. So we are using that symbol. This is R3. That is R2. It is VO2. So if I say that this is V2 under the B condition, that is, this is the condition B, the condition B, this is condition A. Just to make it more explicit, so this is V2A, this is V1A. The voltage here is V1A, and this is V2B, and the voltage here is V1B. So V2B is given by the potential divided root VI2 times R4 by R3 plus R4. And V02 will be given by 1 plus R2 by R1, because it, as I told you, it is a non-inverting amplifier. V1B, that is 1 plus R2 by R1 V2B. And then If I just substitute from V to B, then I can get the value of V02, and then I will just add up V01 and V02. Simple. So that is equal to 1 plus R2 by R1 Vi2 times R4 by R3 plus R4. So that you can also write in terms of resistance ratios, 1 plus R2 by R1 R4 by R3 by 1 plus R4 by R3 times Vi. And then you say the output voltage, the total output voltage with both the sources working is V02 plus V01 plus V02. It is V01 plus V02. So V02 is given by here, and V01 was computed earlier. Here. So therefore, we just add these two voltages, and then it becomes 1 plus R2 by R1 R4 by R3 by 1 plus R4 by R3 Vi2 minus R2 by R1 Vi1. Okay. So a property of the ideal differential amplifier, it is an ideal differential amplifier, the output voltage is 0 when Vi1 equal to Vi2. If V0 has to be 0, I mean not tends to 0, has to be 0. If V0 has to be 0, is to be 0 when Vi1 equal to Vi2, then V0 has to be 0 for an ideal differential amplifier. For an ideal difference amplifier, we can achieve this. We set R4 by R3 equal to R2 by R1. Then this term will cancel with this term. The numerator and the denominator on the left will cancel. The numerator and the denominator on the left will cancel, and this will become R2 by R1 times Vi2 minus Vi1. So the differential voltage gain, which implies that the differential voltage gain will be the differential voltage gain AD will be R2 by R1.
Excuse me, sir. Sir, we have another class.
Yeah, let's end here. So just say that this is the difference or the differential gain. So you see that it is dependent on the resistance ratios instead of AOD. There is no sign of AOD here. The differential gain is totally dependent on R2 and R1 or R2 by R1. So it is totally in my control. How much the output is amplified with respect to the difference between the two inputs, how much this factor is totally in my control. There is no sign of AOD. Okay, so this is what the difference amplifier was sought to achieve, that the difference output should be a magnified version of the difference between the two input signals, and that magnification factor or amplification factor should be dependent only on external resistances, not on AOD. Fine, we just stop here. We'll just take the attendance. Okay, the class is ended. You can leave.